second part. So I think the plan, I'll be talking a little bit about just different layers that are pretty common, really only just 2 layers in the next hour, that are useful across a whole bunch of deep learning applications. And then so tomorrow is going to be a lot of small topics, but kind of for now, these are still, these are the fundamentals, right? After today, then we can cover all sorts of little topics in deep learning, but then we can more or less walk around independently across topics as long as we know these fundamentals, right? So this is basically the end of the fundamentals for now. So the plan. So for all this talk so far in the last hour long, I've only been talking about fully connected layers, right? But then in the morning, I know you read the ImageNet paper, right? And in the ImageNet paper, they talked about convolutional neural networks, right? And then if you read kind of a few years later on that challenge, the ImageNet challenge, there was the Residual Network paper, which also kind of substantially improved on state-of-the-art, right? So these are the 2 kinds of layers that I want to talk about in the next hour, which are foundational in a lot of different, especially computer vision tasks. So convolutional layers and residual layers. Yeah, so that's the plan. So reviewing, this is what fully connected layers look like, right? It's like I'm mixing together all these different kind of logistic regressions. Each of those logistic regressions is looking at all the xi, right? So that's what they mean by fully connected, right? So kind of the picture is for one of these output logistic regressions, I'm looking at all the potential input x's, right? And then since I'm doing this for every single one of those logistic regressions, I have this kind of very complicated everything connected to everything else in my my single layer, right? Now, yeah, also just, I haven't been calling it this, but each of these coordinates is called a neuron in the deep learning literature. There's some interpretation of kind of, if you find a neuron that activates when it sees certain things, then like it has learned a useful representation of what's in that image, right, or what's in that scene, right? So you can think of a neuron as like a high-level feature extractor, right? So that's, but in the end of the day, it's just a coordinate in this feature representation, right? So, and kind of we already saw this formula, right? We're doing this big matrix multiplication where I mix all my weights for each of those regressions across each of my previous layers representation, right? And then I apply a sigmoid to it. Yeah, and then maybe you add a bias if you want. And that's just review. I'm giving you this because I talked about all this derivation about deep learning without telling you that this is called a fully connected layer in the literature. But now, this just so you know the words. Now, okay. Fully connected layers are not what people usually use in modern deep learning. The reason for it, kind of if you go back to this picture, you're connecting every output node with every input node. This is a lot of parameters, right? Even when you have a ton of data, that's kind of a lot to try to fit. And then there's also kind of issues where like maybe this makes training harder, right? So kind of there are a whole bunch of reasons, but in the end, you want to come up with something that's a little bit more parsimonious. And the way that you want to encourage parsimony needs to be in some sort of plausible way, right? Like you don't want to reduce the number of parameters in a way that makes your model much less expressive, or less expressive in a way that would hurt performance. What you want is something that reduces capacity without making certain functions that are important impossible to reach, right? And for a large class of problems, that kind of reduction is to go from a fully connected layer to a convolutional layer, right? You're going to see this reduces the number of parameters a lot without sacrificing kind of the most important structure. And I think before getting into what is a convolutional layer in a neural network, it's useful to think about what is convolution, right? And what's convolution in one-dimensional, or 1D, right? So this is from a wonderful blog post by Kris, so I recommend you check it out. And this is how the story goes, right? What I'm getting to is how do I convolve two functions in one dimension, and then we'll see how it works in 2D, right? So think of this story as I take a ball from some height, and then I drop it, and it can go, in real world it's going to go to continuous, all sorts of positions, but for now I just imagine it kind of goes into k different slots, right? So, and each of these kind of slots, it has a different probability of landing there. Right, so maybe you think it drops and stays kind of directly there, that has pretty high probability, but maybe if it rolls all the way to the end of the room, that's relatively low probability, right? So I can assign probabilities to each of these positions where it's going to end up later, right? And kind of just in my drawings, something I want to try to do is I'm deliberately trying to break symmetry, right? So just for pedagogy, suppose that the ball always moves a little bit more to the right. So in the picture, the branch going to the right is a little bit thicker than the branch going to the left. And the thickness of the branches are the probabilities of having that outcome. Right? So this is just probability. I'm defining some sort of k-level categorical distribution. I have assigned probabilities to each of them. Nothing fancy here yet. OK, this is fancier, but not that much more. So what I do is I drop the ball once, and then I move to wherever it landed, I pick up the ball, and I drop it again, right? And now I keep track of where it went the second time, right? So the way I would draw this is OK, maybe this is the chance that it goes to this one to the right, and then it again can go to any of these positions, right? So this is the chance that it goes one to the right again, or maybe it went two to the left, or two to the left. Right? So you can just draw out this tree of possible outcomes. And then if you wanted to figure out the probability of starting here and kind of ending up here, you just need to figure out all the paths that go there. Right? So basically, this is a device, a diagram that lets you think about the probability of different paths. Right? So even a simple computation, if I want to go right 2 steps and then left by 1, is I go right 2 steps and left 1. I multiply the probabilities, because these are independent events, and I get the probability of that particular sequence. Right? OK. And where does convolution come up? So the way I'm going to get there is that convolution is kind of what happens when you add random variables. But you'll see that in a little bit more detail soon. So in this previous one, I'm showing all the branches. Here, I'm highlighting only those branches that end up one to the right at the end. Right, so how could I have gone to one to the right? I could have gone 2 to the left, then -1. I could have gone 1 to the right and then stayed the same. You get the picture, right? So these are all the ways that I can go 1 to the right after these 2 steps. Now I just erase all the other branches. And OK, this is the formula for convolution, right? And I want you to realize that this formula is exactly the same as this diagram, right? So what is my formula? X and Y are my dropping it the first time, Y is dropping it the second time. U is the position at the end, so this is 1 to the right in this case. So I want to figure out the probability that I end up 1 to the right. Well, first I go k to the right, and then I have to go u minus k to the left. Right? And then I can do this over any of these possible k's. Right? So I can do, if k is 0, then that means I have to go f of 0, and then I need f of 1, because I'm going 1 to the right at the end. Right? And I can do this for kind of any of these possible k's. In this case, there are only 4 of them. So this infinite sum is actually just a sum over 4 things, and it's these products, right? So it's f of 1 times f of 0, right? So it would be like, and then f of 0 times f of 1, and like these are exactly the terms in that formula, right? And the reason for my introducing the symmetry thing, right? What I want you to realize about these paths are that this set of paths is exactly what happens if you flip it around and then rotate it. Or like, you get what I mean? Like first reflect it this direction and then reflect it vertically, right? That's what this kind of lower paths look like for me to make this jump, right? And mathematically, what does that have to be, right? Mathematically, the flipping this direction, that's just turning the k into a minus k, right? When you do f of x and then you do f of minus x, that's a kind of a horizontal, or like a reflection around the x-axis, right? And then the u, what that's doing, that's translating my function, right? So what's happening is I flipped it, and then, I mean, this flipping is not really relevant for the math, right? But just nice for the diagram. And then I translated it by 1, right? So it's not exactly underlying this part, but then it's kind of 1 over, right? So that's what that formula is, right? Yeah, and I think this is a useful way for thinking about convolution, right? Because it tells you something about, if you want to calculate like convolution of two functions, just imagine flipping it and then translating it and seeing how similar they are, right? Because like, or when I mean how similar, it's like, well, look at the branch sizes, and if the branch sizes are pretty big, then that means the value of the convolution is pretty high there. If I had moved my u, if I had translated it by a lot, then in this case there would actually be no branches that match, right? In which case my convolution is going to be 0, right? Because the product of all these probabilities, there's no way to get there. So my convolution is 0. And then you can imagine like all sorts of other kinds of functions kind of playing around with what is the configuration which is going to maximize the convolution. Like, well, if they're exactly underlying each other, so that like the branches have a lot of weight when you multiply them, then that's going to have a high value of the convolution. Right? Okay. This is just, when you see the convolution operator, don't look at it as this mysterious multiplication and summation thing. Just think of it as, drawing these branches and then aligning things. Okay, and then so far I've been thinking about, you drop it and then you drop it again from the same height, it's the same function, but there's nothing about my derivation that required it be the same function, right? I could have dropped it from a very high position first, looked at where it landed, and then drop it from a very low position the second time around, right? So kind of geometrically, what that would look like is my first f function could have gone to all of these possible places, and then the second one maybe only moves a little bit from that first place, because the second time around I drop it from a very small place, right? This is, if you're already familiar with CNNs, then this is already looking like a convolutional neural network, right? Because I'm translating all these smaller filters across a very big function, but we'll get there. But the point is, convolution doesn't have to be just a function with itself. You can do f star g, which is some other function. But then the exact same logic, like draw the branches, align things, and sum up the probabilities of the multiplication, that's the same. Right? So any questions? This is just convolution in 1D. It's basically how you think about summing up two random variables. Yeah. So like if you're summing up more than this, you just think of it as, I have many, many layers in my tree. So I keep on branching, and I'm branching more and more times. So yeah, there's a lot of neat math there. But okay, so in computer vision, right? So people are often using these things for convolution, or called convolutional neural networks. This is a diagram for one of, I don't have the reference. This is one of Jan LeCun's reviews on like deep learning for computer vision. And the first figure in it is this kind of canonical computer vision deep architecture picture. And the picture is always, you have a convolution layer and then a subsampling layer, which I'll talk about. And then just alternating these convolutions and subsampling, and you're building up these feature maps, right? The feature maps are basically the learned representation, like what I was calling these long vectors, you can just reshape them into images or like little rectangles, and that's what these feature maps are. And from a high level, why has this been successful, right? So kind of the first intuition I already mentioned, this is a lot fewer parameters, right? This is going to be easier to train. This is going to be kind of not as over-parameterized as a fully connected network. A second reason for them being successful in practice is that these kind of operations can be computed very fast in GPUs, actually in general. So what I'm showing, it looks like product over all these pairs. So you would think it's a quadratic operation, but it's not. It's actually n log n, and that's deep. So that's like the fast Fourier transform, right? But then, yeah, like through these sort of tricks, you can do convolution very, very fast, and it's much faster than doing a matrix times vector product, which is what you need for a fully connected layer, right? Or a fully, yeah. So that's like a second important reason why this is pretty successful. And then the last is that there's some evidence that what kind of brains are doing is like a convolution kind of in computer vision sense, right? So there's a famous experiment called the Hubel and Wiesel experiment. I don't know if you've heard of this. This is the one where like they show a cat, they've like connected certain of its neurons to some monitor, and then they show the cat edges going in different orientations. And then they show that when the edge is going in one orientation, a particular neuron always fires. But then if you rotate it slightly, that neuron turns off and a different one fires. Right? So there's this idea that in the brain, there are neurons whose job is to be sensitive to different orientations of edges. Right? And an edge detector of a particular orientation is exactly the sort of thing that you would learn in a convolutional filter. Right? So there's already some intuition that maybe trying to mix all these logistic regressions is overkill. Maybe all we need to really be able to parameterize is this sort of convolution operator. Right? So this is kind of the biological plausibility. Okay. And then thinking about image convolutions, as opposed to just, we were doing everything in these 1D sequences, right? So what, like how do I think about an image? I think of it as actually just a function on a grid, right? So if I saw like a picture of mountains, and maybe this one is a little bit darker than the first one, I just raise the value of that whole part of the image larger than the rest of the previous part. And now it's just, okay, this is just some function on a plane, right? And I didn't draw this, but then you can imagine like the tree diagram or like the ball dropping diagram in the exact same setting, like in this setting, right? Where now I drop the ball and it has this probability of landing on any of these grid points, and like a somewhat lower probability of landing on any of those grid points. So it's just the same kind of convolution, the function that I'm doing the convolution over, except it's in 2D instead of 1D, right? Okay, and then that's basically it, right? Like, I had this idea of the 2D functions on a grid, and I now am going to convolve it with these smaller functions, which are like these are functions, instead of like these 4, it would be like a patch on that image. And then I'm going to convolve them in the sense of like looking at the heights of these functions along the paths and then summing up the multiplication, right? So it's basically everything from the previous story, except on 2D, like an image function, and I take the patch is like a small kind of, it can be a predefined function or a learned function. In traditional computer vision, it was a predefined function. In deep learning, it's a learned function. And kind of the canonical predefined functions. So there's a nice example. This is all interactive if you go to this link later. And kind of what they do. So again, this is like functional point of view. Here is, you can move around this little patch, and it computes the convolution. It just some number. So like what I do is for this cell, I convolve it with everywhere around it. And what the convolution is, it's this summation over the branch probabilities, right? So these are different branch probabilities being multiplied by each other. I sum them all up, so that's why these are all being added. I get some number. That number I plug into that position on the secondary image, right? And this is, so right now I'm using a predefined sharpening kernel, right? So what is a sharpening kernel? This is some filter where my function has like a 5, so a very high value at the center of my patch, and zeros on the corners, -1s along the edge. So it's like I define ahead of time one of these kind of filter functions, and I just apply it across the whole image, right? Some other canonical filters, like a blurring filter, right? So if I create like a little plateau and I sum up everything within my patch, it's basically averaging everything across the patches. So when you average everything across a patch, it just kind of smears out the function value. So it gets a little bit blurred. Yeah. It also, you can interpret it as like adding noise, right? Because like adding random variables is convolution, so like adding a blurring is kind of like adding Gaussian noise, say. Another kind of canonical filter, so this is a filter with like a 1 and a -1, so it's like looking for changes like this. And then this is able to detect edges, right? Because whenever you have a drop in the function values, that's going to look like, that's going to have kind of a high product in these branchings, right? So then this pulls out all the edges in the image. Okay, you can't really see it here. But then they're like, there were like really big changes in the tree from the dark to the light. And those big changes from dark to light are being highlighted by this edge filter. Okay. Oh no, I lost this picture. But the point is, yeah, this is, oh no, I think I already had this slide. Skip that slide. Okay, and then the last for the computer vision in the LeCun's diagram, right? He alternates convolution with with some sort of subsampling. And kind of the most common subsampling that people would use is called max pooling. So this is even easier. This is like much easier to understand than convolution, right? All that max pooling does is I take some large image, I define a grid, like kind of even patches across my image. I take the largest value within that small patch, and I populate my new grid element with the value in that patch, or the largest value from that patch. Right? So here, the largest value here is 8 in this green piece, so I put in an 8 in the green piece. And the idea is that this takes a large feature map, it reduces it down to a smaller one. I don't have any like great intuition for why this is something you would want to do, besides that this, again, saves you a lot of parameters, right? So you imagine, well, there's the saving a lot of parameters, and there's also like some insensitivity to local translation, right? So if I translated everything by 1 or 2, then the largest value in that kind of 3x3 patch, say, would be the same, right? So it builds in that. But then I think the main point is like I go from these large feature maps, which need like a lot of filters, more complicated to train, to something that's much smaller feature maps, which are more manageable downstream. Okay, so this is the most common kind of convolution, right? This is vanilla computer vision convolution. There's almost like a cottage industry coming up with different kinds of convolutions, which are useful in different kind of settings. So I think, yeah, I mainly include it for the links. I think the ones that I know the most, so the first two are interesting because they let you do things with natural language. Right? So far I've been talking about images. You can imagine a similar kinds of thing, like here they have a sentence, right? And then they're kind of pooling information from neighboring words by like learning embeddings and then combining them, right? So it's kind of analogous to what we're doing with images, but to get the details right is a little bit tricky. And then those kind of ideas come up in the dynamic convolutions and the causal convolutions papers. Like how do you do convolution effectively on sequences? And then H-Wisp convolution and deconvolution, these are very useful in kind of like computer vision tasks that aren't just classification. So in classification, you have this big network, and in the end, you reduce it down to these k logits, and you make a prediction on one class. But in a lot of image computer vision tasks, you want a response that's very high dimensional. Right? So like a canonical example, like they'll have these, the task is called semantic segmentation. And what they do is you can take an image and you try to figure out like a mask for where is the car in my image, right? And then I'm going to try to shade in every single pixel that is on the car, right? So for that kind of task, the output is a large image where the value in that pixel is the label for that pixel, right? So in those sort of tasks, you need to have large feature maps all the way through, right? So this sort of architecture falls apart in that setting because here the feature maps are getting smaller and smaller every step, that by the time you get to the end, it's going to be tricky to kind of get a large image again, right, in your prediction step. So in those sort of situations, the things that you need to do, either you do H-risk convolution, which is this idea of, it's basically have a larger convolution map. So yeah, they have a picture here. It's like what you have a larger convolution like receptive range, but then you just zero out some of the weights in between. So like you don't try to learn all the weights in that large field. And then the idea is this is not reducing not reducing the receptive field very much, but then not requiring as many parameters as a naive convolution with that large receptive field. It's basically letting you do large patches without having to learn all the parameters for that patch. So that's the H-risk convolution idea. And deconvolution is basically, I take one pixel, and then I turn it into 4 pixels, say. So like the most naive way is just copy that same original pixel 4 times. I just kind of upsample my image. But you can do it in a smarter way, right? Because averaging is a kind of convolution. You can think of this as like the reverse of averaging, this upsampling operation. You can do the reverse of convolution, where like I start from this one pixel, and then I might convert it into a slanted thing over that patch that's centered at the original pixel value, and that's a kind of deconvolution operation, right? So this is a way like you can learn the deconvolution operations in the same way that you can learn the convolution operations, right? And this is a way of going from small feature patches to larger feature patches, and whenever you get since you get to larger feature patches, that makes it easier to do computer vision tasks across whole images. So I'm mainly including it as a reference so that you know in the literature, these are kind of, whenever you run into large image computer vision tasks, you'll see these words. These are references for those convolution types. But there are many, many kinds. And again, it all works because you can design a new convolution layer, and as long as you know the derivative of the output of that layer with respect to the input of that layer, you can plug it in anywhere in your graph. Okay, and then last, I want to talk about residual networks. So this is kind of the dilemma that literature tries to face. On the one hand, it is, at least up to this point, they had documented the deeper and deeper you got, kind of the more meaningful the features seemed to be, and the better your performance was when you got it to work. But then it was much harder to get it to work. Either it was much more training, it was much more sensitive to hyperparameters. It was one of these things that people imagined should be possible, but it was really hard to get to work in practice, right? So that's the dilemma. And kind of like abstracting that away, what is the problem? Kind of the insight that the people who came up with the residual network paper had is that, let's say like the purple is your current guess, and you're trying to approximate black, right? One thing you can try to do is learn some like a full function-to-function mapping. But this is complicated, right? Like it's hard to get it exactly right that this is going to decrease, this has to increase a little bit. Like it's possible using kind of a series of deep learning layers, but it's a little bit trickier, right? Compared to, let's just try to model the difference between the functions, right? So the idea is I look at the difference between these two, I plot that out as some new function. And the idea is that this new function to learn might be simpler than the kind of full function-to-function transformation. And this is especially true when, let's say the two functions were actually equal to each other at a large part of the range, then this new function is mostly 0 for a lot of places. And whenever it's mostly 0, that's going to be easy to learn, right? Because you don't need as many weight updates to tell it that it's 0. You don't need any weight updates if it's exactly 0, right? Versus if I'm trying to copy one function to another function, even if they're exactly identical to each other, that's going to require weight updates, right? Because I need to learn a new layer which is exactly copying that previous layer, right? So it's easier to learn modifications in a sequential way than learning to kind of recreate the previous function from scratch each time. So that's kind of the essential intuition. Now, the trouble is, how do you encode this mathematically? It's actually not that complicated, but there's some subtleties. Okay, the first thing. Here's an attempt. I'm trying to go from the k-minus first representation to the kth representation. What might I try to do? I mean, the first thing you do, this is a slightly more general but the usual, you just do w times h, but maybe you can do other kind of operations on w and h. But you have some function of w and h. But then instead of just doing this, which is what usual deep learning would do, you add in the previous thing, right? So now this is concretely this idea that I only need to learn the difference between my two functions, right? I only need to learn the difference between the two representations. And this is much more straightforward than directly transforming the original function to the new function. Right? So this doesn't immediately work, though. So this is a little bit subtle. Is it clear to anyone right now, actually, why this might not work, or why you might want to do something different? Basically, this thing is like this diagram without this intermediate, or without this final mixing operation. And now that I want to add in this extra mixing operation, I just add in that final, that next weight layer. And then since I'm adding kind of this, whatever weights are learned by x, I can have this kind of skip. Right? So this is the diagram from their paper. Okay, and why is this useful? Kind of the main advantage is what used to be very finicky to train can be done much more straightforwardly, right? Somehow, and this is still a little bit mysterious to me, but maybe I'm sure there's people working on theoretically why this might be better. But the idea is the operations you need to do gradient descent on these kind of residual updates, it's much more straightforward than the updates you would need to do these kind of full function transformations. So you can train much deeper networks, and these deeper networks do much better in competitions or in practice. So this is kind of the diagram that they showed. You have this kind of original implementation of one of these ImageNet competition datasets, or ImageNet competition problems. You don't have as many layers in that ImageNet competition winning solution. They just tried, okay, let's just make it really, really deep and see what happens. It's almost it's like the joke about deep learning. It's what is the key to your success? Well, if you just make it more and more deep, that should work, right? And no, this does very badly. It actually is impossible to train. But then if they add in that kind of module that they had defined in the previous part based on their kind of analysis of the residuals, then it becomes trainable, and then it beats the previous by a bit, actually. Yeah, and I think that's the main parts. I especially wanted to cover convolution because in kind of tomorrow we'll talk about it a little bit, and I know some of the more applied lecturers are going to be talking about convolutional networks a lot. And I wanted to mention residual layers because kind of most modern, most modern deep learning applications are using residual layers at a lot of places, and just know it's not that much different from the original kind of deep learning framework, just it's learning these differences, so I think it's worth mentioning. I didn't really get a chance to talk about these other kind of layers, but these are very important, especially if you're doing something sequential, right? Attention, LSTM cells, gated recurrent units. So these are going to be, whenever you're working with like text or language data, these are useful. And feature-wise modulation, this is an idea for if you want to work in settings where you want to introduce some sort of external conditional information, you can use feature-wise modulation. But this is more just so that you know that they're out there, other kinds of layers that not as common, but then in particular settings can be very useful.
Thank you. So just want to say that I'll be covering LSTMs, GRUs, and attention, some of the attention when I do NLP. That's coming towards the end.
Okay, I have one more.